All right, guys, I just wanted to make this quick video for everybody because I know that this lab and the upcoming two labs on optics stuff are going to be really confusing, especially since you are not even starting this stuff yet. This is going to be hard. So I'm just going to record these quick videos that will be in addition as supplements to the videos already posted on Long Kappa. Because I think it'll be helpful, all right? Because there are some points in the video that I think he goes a little fast over that will be confusing to you if you don't know it. So I'm just going to quickly go over stuff that I think is relevant. This stuff I wrote up today from today's lab, in-person lab, I mean. I'm just going to record what I wrote down, basically. So look, today's lab is observing the following. We have a surface that's the boundary of two different materials. Let's say this side is air and this side is water. Okay, that's the first part of the lab that you will see. All right. What we're trying to observe is what happens when we shine a laser. What are all the different rays that come out of that, and what are their angles, and how do they relate to each other? Okay. Here's the thing to realize. Okay. Whenever there's light, whenever you shine light, for example, a laser onto some kind of boundary between two materials, some of that light is reflected and some of that is transmitted through. Okay? And this is actually a property of any wave, like sound, like waves on a rope. All sorts of waves are like this. And light is an electromagnetic wave, which hopefully you will learn in class at some point soon. But anyways, because light is a wave, some of it is reflected and some of it is transmitted through any boundary between two mediums. Okay? So air and water as an example. Okay? Or the other way around. Now with this scenario, I note down 4 different things that are important, okay? And I want you guys, whenever you're trying to analyze or understand what's going on, I want you to note down 4 things. You're gonna have the light ray coming in. We call this a ray, okay? And all of these lines that represent light, we call those rays, okay? The light that's being shot in, that's called the incident ray, all right? That's the light you're aiming from a laser, you're shooting into it, all right? Into this boundary. And then that light that's reflected, we call that the reflected ray. All right, and the light that's transmitted through, we call that the refracted ray. Notice that's refracted, this is reflected. They're almost the same spelling, but they're different, okay? You may, if you want, call that the transmitted ray. If you want, that may be more helpful, okay? So we draw out these 3 rays. So note down these things. The other thing I want you guys to always draw, this will make things a whole lot less confusing, is this normal to the surface. So here's your surface. Draw a line perpendicular to the surface. We call that the normal to the surface, okay? Note that down. This normal, that's how we measure the angles, okay? And that will make things a lot less confusing when you're trying to write out the angles for everything. Use this, okay? Now with this setup, we have 3 angles we're interested in. We have the angle of the incident ray with respect to this normal. We're going to call that theta 1 or theta I. You'll also see that in your lab manual. We have the angle of the reflected ray with the normal. We call that theta R or theta 1 prime. You might also call it that. And we finally have this angle of this refracted ray or this transmitted ray with respect to that normal. We'll call that theta 2, or we can call that theta T for theta transmitted. You'll also see that in the lab manual. Now all this lab is about is investigating the relationship between these rays and their angles. And how can we relate them? Can we predict, for example, what the refracted angle will be if we know the material and we know what the ray coming in, what its angle is with respect to the normal? And indeed we can. We do have some laws guiding the relationship between these angles. So a long time ago, people experimentally did all this stuff and they wrote up some laws relating all of them. And the first law is the law of reflection. That says that the angle of the incident ray is equal to the angle of the reflected ray. With respect to this normal to the surface, they're going to be the same. So angle of incidence equals angle of reflection. And indeed, this actually not just guides waves of light, which is what this is, electromagnetic waves. This also guides sound waves and a whole lot of other waves. So that's a very interesting thing. I think it's kind of wonderful that it comes out as simple as that. Just angle of incidence equals angle of reflection, okay? The other law, which is a little more involved, but it tells us, so this gives us 2. It gives us what the angle of reflection is if we know the angle of incidence. What about this other angle, this angle of refraction or angle of transmittance? What is that going to be? That's what Snell's law tells us, okay? That's this over here. And now I'm going to say the way it's written in the lab manual and in the video is wrong. At one point, it's wrong and it will give you the wrong answer. Okay, so be careful of that. I'm going to send you guys an email also noting this. But Snell's law is what relates the angle of incidence to this angle of refraction. Okay, and this top part is the law. Write this down. This is, I think, a whole lot easier than what's in the lab manual. In the manual, you have this. Okay, I think that this is okay, but it could lead to a confusion, especially this part. Notice we have 1 and 2, 1 and 2, and then oh look, 2 and 1. Some people might not notice this and they will do 1 and 2 and then it will be confusing and you'll get some errors. So write this top part down. This is N1 sine of theta 1, N2 sine of theta 2. Now what does this N represent? That's what we call the index of refraction. Remember when I was drawing out this scenario, I noted down that these are two mediums. This is the boundary between two mediums. One medium is associated with the incident ray. The other one is associated with the refracted ray. We're going to call the incident ray's medium N1, and we're going to call the refracted ray's medium N2, or at least their index of refraction. Okay, so there are two mediums here. So that's why we have N1 and N2. Now N, okay, that's what we call index of refraction, and that's basically telling us how, it gives us a way of saying what the speed of light in that material is going to be, with respect to what the speed of light is in a vacuum. So first of all, what is the speed of light in a vacuum? That's 300 times 10 to the 6 meters per second. Okay, you can look that up on Google, and that's something that maybe you at least have seen at some point in your life, that the speed of light is 300 million meters per second. Okay, that's the speed of light in a vacuum, okay, when there's no medium at all. It's also pretty much the speed of light in air. We consider air as an almost vacuum of sorts, and we've seen that many times actually throughout this course. So that's what the C is, okay? That C is the speed of light in a vacuum. It's around 300 times 10 to the 6 meters per second. This V over here, this lower V, that's what the speed of light is in the material you're talking about, okay? And what we'll find is that the highest that light will ever be in terms of its speed is in a vacuum. That 300 million meters per second, that's as high as it's ever going to be. As soon as it goes through any material, it's going to slow down at least a little bit. And depending on the material, we'll get different speeds. So just as an example, for water, we're going to find that its speed, the speed of light in water, is something like 260 million meters per second instead of the 300 million meters per second. So that's what that V over there will be. That's what the speed of light is in that material. And then the index of refraction is ratio of speed of light in a vacuum with respect to the speed of light in the material. Okay, and this is an example here. For water, it's 1.33. Okay, notice, by the way, 1 means that the material, the speed of light in the material is the same as in a vacuum, as in that material is pretty close, approximate to a vacuum. If the index of refraction is really high, that means the speed of light slows down by a lot. Remember this again, I'm going to say it one more time. If the index of refraction is high, that means the speed of light slows down a lot more in that material. Okay? It's a little bit of an inverse kind of thing. I think the way they defined index of refraction is, in my opinion, confusing, but that's just how it is. Okay? So just remember that. Index of refraction, if something is higher, then it means that the speed of light slows down in that a lot more. So for example, for water, the speed of light slows down by a factor of 1.33. So if you take C, you divide it by 1.33, you get the speed of light in water. Okay, so that's what the index of refraction is. So back to Snell's law, that's what explains this N1 or N2. This is the medium of the incident ray, medium of the refracted ray. And then you have this law guiding the relationship between the angle of incidence and the angle of refraction. Okay? Using Snell's law, we can now derive this stuff. And that's it. That's all the laws you need for this lab. That's all the equations. But it will be nice to note and explore this law a little more because we find some interesting, let's say, phenomena as a result of this law. So let me go ahead and rewrite this law. I'm going to write it in this form over here, okay? That's just dividing N2 on both sides, and I get that, okay? Now we see 3 different scenarios, okay? And in terms of the materials that you pick, okay? So I wrote these down, okay? And I think this is not in the lab manual, but this is very helpful, in my opinion, okay? So if the materials are the same, so N1 equals N2, so material doesn't change, then guess what? Sine of theta 1 equals sine of theta 2. And essentially what that's saying is that the angles are going to be the same, all right? That the angle coming in is going to be equal to the angle going out. That incident angle is the same as that refracted angle. One more time, just to remind everybody, these angles are with respect to the normal, okay? So always draw the normal first and then measure the angles, and that will be very helpful to and minimize confusion here. So if N1 equals N2, the angle doesn't change and light just passes through, no problem, okay? Now, what happens if the index of refraction of the incident ray material is higher? So if N1 is N2 is greater than N2, what you're gonna find is light speeds up. That's what this means, okay? If, like I said, that's why I repeated this many times over here. If a material has a higher index of refraction, that means light slows down a lot in that material, okay, compared to the speed of light in the vacuum. So if the speed of light in N1 is smaller than N2, that's what the N1 greater than N2 is. Remember I said this is kind of an inverse thing. That means that once light crosses from one material to the other, it's going to speed up, all right? And if it speeds up, that means that sine of theta 2, based on this over here, if N1 is greater than N2, then sine of theta 2 is greater than sine of theta 1. What that's telling you is that theta 2 is going to be greater than theta 1. And the way I like to think of this is if light speeds up, it wants to point away from the normal, okay? It wants to point away from the normal. So if light speeds up, we point away from the normal, okay? That's going to come important in a second. Now, the final scenario, if N1 is less than N2, so the speed of light in the first material is faster than in the second material. In other words, light slows down, okay? If that is the case, then again, using this same thing, we get sine of theta 2 is less than sine of theta 1, which means that the angle of theta 2 is less than the angle of theta 1, which you can see there. And that means that, and I like to think of this as the light ray, once it transmits through, it wants to point towards the normal. It wants to come closer to the normal. Here, when light sped up, it was away from the normal. Here, when light slows down, it goes towards the normal. All right? These are your three scenarios, your three possible scenarios with Snell's law. And I think if you wrote this out and you have this in your mind, it's going to be really helpful in class as well as for this lab. One last thing I want to note is all our angles over here, theta 1, theta 2, and this theta 1 prime, all of them have to be within 0 to 90 degrees. So we will never have the case where the light ray coming in here comes out in this area over here. It never happens. It's always at least a little bit forward from this line. So we never have theta be negative, and it's also never greater than 90 degrees. Okay? So that's a constraint. With this observation, we have Snell's law. These are the kind of outcomes from it. So hopefully, this is the fundamental kind of material for this lab. We will explore one extra thing in this lab, which is this scenario over here. Okay, so note over here, I said when light slows down, it points towards the normal. The most it will ever be is exactly in line with the normal, and that's that case there. That's that case where light slows down. So if N1 is less than N2. However, what happens when light speeds up? We said it points away from the normal, right? Well, there is a certain angle that if you shine that angle in from here, at some point, this refracted angle, it goes all the way to 90 degrees. And then after that, it actually will go past and it will be purely reflected. And that's what we get over here. Okay, I wrote this out over here. So we have only in the case when N1 is greater than N2. So the speed of light will speed up once it goes through the material. Or in other words, when the index of refraction of the incident material is greater than the index of refraction of the refracted material, only in this case do we get this pointing away from the normal. And there is an angle such that for theta 1, such that the angle of theta 2 becomes 90 degrees. That's what we call the critical angle. Okay, that's for theta 1, the incident angle. There's a critical angle. At that point, we can calculate that that critical angle is this. That's just applying Snell's law, using for theta 2 90 degrees. We can solve for the critical angle, and that's what that is over there. Once we hit the critical angle, guess what? We used to get something like this. Once we hit the critical angle, we get no more refraction, purely reflection, purely reflection. There's no more light that transmits through. All of the light gets reflected. Okay, remember, it's always the case that we have some light reflected and some light diffracted. Okay, that's generally the case. However, in this case with N1 greater than N2, we no longer have any refracted light, purely reflected light. Okay, and that's the equation for the critical angle. In the manual, it mixes this up. In the manual, it says N1 over N2, which is wrong. Okay, please correct that. That is a mistake. In both the video and in the manual, they have that wrong. Okay, so with that, you should hopefully be able to go through the lab a little better. That's the material covered for this lab. Okay.